Welcome to a pair programming session with LeBlanc Meneses. I'm going to show you how I go about building um, a math equation solver using my open source tool NPEG, which is .NET Parsing Expression Grammar. My goal here is I recently made some commits on GitHub, and I want to push the updates on a new NuGet, and I'm building the package right now. But in the process, before we only had a Boolean algebra solver, and now I'm gonna add the math equation solver. And before I do this work, I wanted to kind of tape it so that someone that wants to use the actual framework understands how I go about building these parsers and evaluators myself with the tool that I built. So, a couple of things that you're going to need to get started. When you install the NuGet package, you get the sample. Right now, initially the old version of the package that I have out there was only had the Boolean algebra solver. I'm going to show you how we're going to build this one right now. What I've done is I copied these into this folder. I fixed the namespaces a little bit, but as you can see, this math equation solver still has that Boolean algebra stuff that I need to replace. The AST evaluator has the same concept of find variables, solve equation, but it's still, again, specific to that Boolean algebra. And then the parser, I removed the grammar because it doesn't make sense anymore. So this is a tool that I've released. You can download it. You can click on it on the GitHub page, and it'll send you to my website. And you can right-click and install from the website, and you'll be able to have a desktop version of this tool. What's nice about this is it puts this, given your grammar and given some text input, you're able to run it, and on the right here it'll show you these rules. Excuse me, it looks like it's running in the background. Um, these rules here are basically represented inside this parse tree here. They're the exact rules that you've written in this specific in this tree here. And then you have the actual abstract syntax tree, which is the text input broken down by your parsing rules, which is the grammar rules here. And you can see that your text input, I have this one commented out, but this input here, so S is white space, and that's why the comment is listed under S. And then you have the real things that you're looking for, which is a cosine, and then it says that it's internally has other nodes that represent the rest of the data. So the trig represents the cosine, and then you have this digit here that represents the number, and then the symbol that represents the plus. And it's in hierarchical order based on your grammar rules here. So this tool will let you know what nodes you need to build inside the visitors, and kind of where you're going to grab the values from. So instead of looking through all of these and manually figuring it out, this tool will let you know, well, you need if you want to handle white space, you need to handle S. If you want to handle any trig function, you need to handle this trig node. And if you want to handle numbers, you need to handle this digit node. So that's what this tool is useful for, to tell you kind of what, given input, how is it going to be represented inside this abstract syntax tree. Alright, so let's go back to code. Oh, that's something I'm actually working on right now. Let's work on the old Visual Studio, this trash app here. And let's grab this input here. No. Alright, so we have the same grammar rules that are in by default in the tool that you download, and it's represented by this parse tree here, and we can see an example of input being passed to it look like this. So we're going to grab both the rules, the grammar rules, and the actual input, so we can see the same AST. Okay, so parse tree is done. So the parser is done. All we have to do is copy the grammar rule, and the framework will take that and build what you see on the parse tree. And then now we need to focus on the actual AST and the actual salt. Yeah, basically evaluating that AST. So this part, the parser is pretty easy. You just grab it from this language workbench tool I have. The next thing is the actual input. So we come to the solver that kind of sets everything up, and we're going to put the input here. So there you go. There's the input. And this is things that we're going to figure out in a minute. Let's go to the actual. Let's go ahead and set this up though. Boolean algebra solver, okay? And then we'll have the math equations. This one here. Okay. Order two. Okay. And this one actually, we don't have actual find variables. We only have, so we're not actually looking for variables to do replacement on. So I can actually remove and just go straight to solve equation. So let's go back into this runner and remove the section for the Boolean algebra that was finding variables, because we don't need that anymore. All we need to focus on is the actual evaluation. And let's see. We don't need this anymore. So right now I'm just refactoring the previous code and removing what I know I don't need anymore. Okay, so that looks about right. And we're not going to need this anymore. We're going to be able to get the output directly. We're going to pass, give it the input. Let's call this bytes. Input. And now we'll be able to pass and show you the input, and then show you the 0. No, okay. So evaluates to. So there you go. When this runs, it's just going to print into the output window the equation that you provided it and the actual result that was evaluated by this engine here. Okay. We don't need to put that. Okay. So it looks like we're done with setting up the runner. Now we actually need to focus on just this solve equation here. So we'll take that from from here. I'm gonna focus on everything right now. You have to make the decision on whether you need to handle the visit enter. So as each one of these nodes are the product, the trig, the expression, the sum here on the right. As each of these nodes are entered, this method is going to be called, and you can grab the name based on the token name here. So example, this eventually going to say we eventually want to focus on trig. We eventually want to focus on that node. We eventually want to focus on digit and symbol, and that seems to be what our major focus is on. That's just going to be easy, and we're not going to be handling white space because that's just it doesn't concern the evaluation at all. So now you just need to figure out when you want to call this. When you're building something with the visitor like this, you're normally going to be using a stack. So normally when you're entering methods, it's useful to have this stack to hold the results, so that when you leave the node, you you can pop it out and you'll and be able to evaluate all these symbols when you're leaving the actual node. So when you enter it, you normally populate your stack. When you leave the node, you remove the items from the stack. It's kind of how you need to approach it with when you're using the visitor approach. So you're always having to maintain the stack yourself, and based on the enter, you're adding it or you're removing it. So we're going to be handling these nodes in both of these cases. So in the stack, I'm going to be storing, let's store double. This is going to be the actual result that we're storing. And we're going to change this to double. And when you're at the very end, basically your peak is going to be, the stack should only contain one item at the very end, which is the actual answer that you have. So actually for enter, since we're populating that stack, I think all we need to handle is digit for this case. So we'll say results push, and we're going to do double.parse, and we're going to be guaranteed that it's going to be a double based on our grammar rules. So there's no we don't need to do a try parse or anything like that. We're going to be able to node token value and then pass in the input iterator. And this is actually an extension method to grab the value. Otherwise, you will need a call from the input iterator called getText or text, and it's a method to give it the starting and the ending index into that byte array to get the actual value. This is to conserve memory. And that's one of the latest changes I've done. So I used to have value property, but it would basically double them. I mean, increase the memory by quite a bit because of that. So now I'm grabbing it straight using this extension method, using the iterator to grab the value when I need it only, and not persist it on the actual token. So here you go. We're pushing that specific digit into the results, and only when I leave, when it's a symbol or when I'm trying to calculate this trig, will I pop an item off the stack here. So for trig, it's going to be quite simple because I'm expecting an expression, and the expression should have by this point already pushed that item into the result here. So for trig, I'm just going to evaluate the actual node token value. Let's actually, yeah, that value. Input it. I'm expecting the symbol cosine to be on here, so all I'm going to do is say string that starts with what happened? String starts with starts with cosine invariant. Okay, so if it starts with cosine, it's going to fall into that condition there. Else, if well, let's copy this a couple of times. And let's come here and let's look at the grammar rules. So I'm only handling sine and cosine right now. You need to add the rest of the trig functions that you want to handle. So I'm only going to handle sine and cosine for now. But if you can see here, this sine here, we can make it to where it's case insensitive. So right now I wouldn't actually have to have this ignore case because by default the original grammar wasn't handling was case specific. So by adding this switch here, I make the string case insensitive. But I'll go ahead and do it for future because I think I eventually will change it. Actually, let's go ahead and change it in these rules here. The parser. So there you go. We'll make it towards case insensitive. And we're going to be handling these two nodes only. So we're going to do math dot cosine, and then we're going to pass in the results dot pop, and then we're going to basically push it back in after it's been evaluated. Push. And then we'll do the same thing for this one here. And this one will be sine. Nope, not that one. Sine. Okay. Results. Oh, there we go. And then we'll have digit should have already been handled when it's entered. I don't really need to handle when it exits. Not that I can tell right now. And actually, and then we have this symbol here. And you notice that symbol is between two products here. So basically, when we get this symbol, we're gonna be able to pop two items off the two values. We're gonna be able to pop this one, the left, and we're gonna be able to pop the right. You see. let's go ahead and make this a little bit more tougher here. It's actually 15. This is a cosine. This one. Let's look at this one. So there you go. Symbol. So from looking at the AST, I really can't pop out two numbers and then use the symbol here, because this node comes, the symbol is in between. It hasn't evaluated this product. So this product's been done, this product hasn't been done. So it looks like I'm not going to be able to use this specific symbol here to actually do that evaluation. I think I'm going to have to go off of these here, because these are actually what matter. Sum and product. So that's what I'm gonna do. I'm gonna go off of sum and product. So we'll come back here and we'll change this to be sum. Change this to be product. Actually, I'm gonna take this here because this is going to be kind of similar to what I'm gonna need to do up here. So I'm gonna check to see if the results has more than one item. If it's greater than one, then I can safely pop two products and multiply them together and then store the results. And these are doubles, so let's just change it to var and then we'll be done with that. And I'm only going to be working with, this is, based on the grammar that I've written there, it's going to be inside the plus and the multiplication are done in by the terminals that you have here. So we actually don't need this. We just need to be able to push the result back in. This will be multiplying. And if not, then we're going to actually ignore that node. We're not going to do anything with it. And then this one should do the same, but should add it. I think that's all we actually need for this evaluation here. Let's. I'm curious to know if what if it'll give me. Let's do this. Assert results that count equal 1. Okay. And let's go comment this out. We're not interested in running this right now. See what we hit. Let's see what we get. Perfect. It's one result. Now I just need to calculate that in my calculator, make sure that what I provided is actually correct. It says that this is the actual value, and let's actually check it with the calculator. Great, my calculator is dead, so I'm gonna pause the video and actually get some batteries for this. Actually, we should be able to solve this. Have Visual Studio open right now, so might as well solve it with expected math cosine 25 plus cosine math cosine plus 3 R result expected. Given that input, this is what would be expected. Expected 2. Alright, so let's try this again. Oh, well, let me set them. Okay, we're about to evaluate this. Ooh, it's not the correct result. So now we need to figure out, this is where unit testing would be helpful. Figure out why that problem is. We need to store this symbol somewhere, and that's something we're missing in our system. And same thing with the product. We don't have any division here, but we could have. And in our grammar, we're saving the symbol, but we're not doing anything with it right now. So that's one of the next things I want to add before we get into the figuring out what this expected result. Let's finish the. Let's assume this is correct for now, and let's add the symbol first. So we need a handle symbol, and we're going to store that in a different collection symbol, different stack. Let's make sure we get the spelling correctly. Symbol. Yep. Okay. Break. And we're going to store this in a symbol. Let's just say it's a car. Symbol. Okay. And here we're going to just push it on the stack. Symbol that push. And what we want to do is get the value of a node when it's here. So we get the value, which is going to be a plus, minus, multiplication symbol, a division symbol. That's what this is giving us a string, and all we need is the first character. And by definition, these are cars. They're only one character strings. So we're going to be able to just get that one character right now. This is the symbol nodes. Come back here to the project. And now the sum and the product need to take into account the these symbols. So rather than assuming this, maybe we can assume it based on the symbol count. While symbol dot count not equal to 0, because we expect this symbol count when we leave a sum or when we leave a product to be completely 0 at each of these once they leave these nodes. As we can see here, if we're adding these nodes together, I expect two symbols to be there. So when I'm done with these two symbols, the symbol stack should be 0. So before we continue, I want to clarify something about the visitor. Here we have this visit enter and visit leave. And how do you know where to put the actual when you want to actually handle a specific node? Do you want to do it on the enter or on the leave or on both? How do you know when to make that decision? One way to do this is if you look at the syntax tree here, the abstract syntax tree, you'll see that there are nodes that will never have any children. Example, the symbol node doesn't have any child nodes inside of it. So you know that this node here, it doesn't matter whether you handle it in the enter or on the leave, because you're not waiting for it doesn't matter. It's only one node the whole time. However, for this sum and product, the decision that decision is important, because normally when you're maintaining a stack, you want to add some stuff to the stack, and then at the very end, when it goes through all the children iterating visit enter, visit leave, visit enter, when it comes back, when it starts to leave all these nodes, you want this product node to basically do what it's supposed to do, which is to take a product. So that gives you an idea. If it has child nodes, you're probably going to handle the visit leave. If you don't have any specific child nodes, it doesn't matter whether you put it on the leave or on the enter. The enter is useful when you want to do something before entering these children, but normally when you want to evaluate something, you want to do it when it leaves all the child nodes, so you can take the result of the child nodes. So that gives you an idea of when how to make that decision on whether you want to include this node on the visit enter or on the visit leave. I'm gonna go ahead and, since it doesn't matter for the symbol, I'm gonna go ahead and move it up into this, and you'll notice that I already have digit here, because again, when I made the decision that digit is only going to have a number in it, and it's never going to have any child nodes inside of it. It's a terminal, while these are handling non-terminals, meaning they have child objects. Okay, so we've changed these to while loops so that we make sure that we're taking into account the symbol, and as we leave a sum, we want to make sure that the symbol count goes to 0, or when we leave product, the symbol count goes to 0. So let's go ahead and change this one here also. What we'll do is we'll do it this way. Var result equal, or some result equals to 0. And Since we're doing them one at a time, I want to do it like this. And at the very end, I'm just going to sum these results here. I'm just going to add the result there. Oh, let me make this double. There you go. And we'll do the same thing for the product. And we'll make this 1 so as it multiplies, we're not initially changing that value. Product result equals and then actually this needs to be multiplication. Oh, actually we need to take into account the actual symbol count. So let's do that. Result. And when it pops, the actual symbol is going to be a car. So all we need to do is compare it to product. Else, actually let's use a switch statement for this. And let's do case break. And let's change this to division. And I think that would be safe to do result pop. We expect 1 to already be on there. If there's no symbols in between them, then symbol count will be 0, and so the product result just gets pushed back in. But if it does have symbols, it'll go ahead and do the multiplication or the division. And we'll do the same thing for the sum. We'll copy and paste this piece. Let's just copy and paste this whole piece here. And we'll say sum result and we'll do plus and we'll do minus and there you go. This should handle the symbol appropriately. So this doesn't handle this expected value yet. We're only handling that. We're now taking into account the actual symbol that's written in the expression before we made some assumptions. Let's go ahead and run it and see if we actually get a different value. This is what we had before. Let's see what we get now. Oh, what does it say is we didn't capture it, so uh, actually what we can do is do node children was a digit. Let's go ahead and save this. Let's find out where this is throwing an exception. Interesting, we have we're inside the product thing, but we have plus sign. I think I know what the problem is. Let's just rerun this. So we have one of these digits. Where is the symbol? Let's look for the symbol tabs. So at this point, we've added an item into this. An item into the symbol stack. We then enter the product. We add another symbol here. Let's run this again. So it's 15. So when 15 is popped off, it throws an exception because a symbol is already, this symbol is what's causing the problem here. So we can't assume that So what I'm going to do is, this is one example where when we enter this node, we need to start a new stack for symbol. This way when we leave the node and example, like when these are the symbols that need to be calculated by this sum. So this specific sum here should have two symbols. This symbol in here needs to be handled by this sum here, not by so what we need to do is be a little bit smarter in terms of maintaining that stack rather than it being global like it is today. Maintain it on per as it enters the sum and product node. Sum There you go. So here we'll start a new stack each time we enter that, and we'll push new stack, and we'll push when we enter the product. So each of these will maintain their own stack as when you enter the node. So when you leave, we'll know if there's any symbols which requires us to do a calculation, and that will be done on the leave. So the symbol value. There you go. And then this needs to be done the same up here. Let's just say okay. Product pop. Cool. So now let's see the result of this. Okay. We just need a do symbol peak, so we can get the stack of the current symbols, and then we're going to push onto whether we're inside a sum or a product, the actual symbol. And now let's see. Alright, so we're now able to evaluate that, and we get the actually we're now done, because now it's properly calculated after we've added the ability to do the symbols. I just don't understand how. Okay, so this is what we calculated now with the introduction of the properly handling symbols, and this is what the expected value is. So actually, just by finishing up that grammar, we were able to fix it automatically. So we didn't have to do any more debugging than just finishing up the grammar inside the abstract syntax tree. And this is how we went about building the actual evaluation for the math equation. The last thing I want to talk about is the two let's see, you get NPEG. The two different packages I have on the on NuGet, and let's see if I can click on this name. So let me right click on this. So actually it says on the description, this is the offline version of one is an offline version, and what I mean about the offline version is you won't be able to use the actual DSL like you do here. If you want to use this here, you have to use this first package here. If you want to use the offline version, which is exported example, say I wanted to export this in any specific language. Right now I'm going to do C#, just because people watching this are going to be developing in C#. But if we wanted to get the offline version, you would, let's say, let's store this on the C drive. And temp. Let's language workbench. And then let's go to the C drive, temp, and unzip this. This is the offline version. It prints out what your grammar rules were, and it gives you the actual offline version that doesn't do any interpretation of the grammar rules. It just gives you the output of this parse tree that you see here on the right, and this will reduce having to do that during your application during runtime. It's already pre-evaluated or compiled into the language rather than having to go through that interpretation step. Those are the differences between the two packages that I have on UGET right now. Thanks for watching, and I hope to see other people using these libraries to build some interesting domain-specific languages.